Any questions? Everyone happy? So what we're going to do now, I'll just erase this because we're going to use this section to work through an example, and then using that example you'll have a crack at doing this on your own, and then we're going to collate all our results to see something somewhat interesting geometrically. So I'm going to take the example of z to the 3 equals 1. So let's work through this together. So what do we know right away? How many solutions are we going to have?
3.
3 solutions. And what I might do is I might just over here plot up a very simple Argand diagram. So we'll have our real axis and our imaginary axis and our origin. I'll just do my best to kind of draw up a unit circle. So I know that there's basically 3 points I want to plot on this unit circle, and what we're going to do is follow this procedure to work out what those 3 points should be. So what's step 1? We're going to let z equal cos theta plus I sine theta. Therefore, z cubed will be cos, and what do I put in this angle? Anyone want to yell out? 3 theta, that's right. I'm bringing the n down into the argument. And therefore, using this step 2, we know that that's going to mean 3 theta will be 2 pi k, for k being an integer. So therefore, we want values of theta that is 2 pi k on 3, but specifically in the domain of negative pi, theta greater than negative pi and less than or equal to pi. So what can we do there? Any thoughts? How do I work out what values of k this will be true for? I've got an expression for theta here. I've got a theta in this inequality.
You can put in values.
I could, yeah. And actually when we're only dealing with 3 solutions, that's kind of not a burdensome thing to do. But actually, when we're dealing with bigger and bigger numbers, the process to follow that's always going to serve you well is you take this expression and you throw it in the inequality. So what we're going to say is negative pi will be less than 2 pi k on 3, which will be less than or equal to pi. What's common to all of these parts of the inequality is that there's a pi. So I can essentially say that they all cancel. So we can say negative 1 is less than 2k on 3, which is less than or equal to 1. And I'm just going to rearrange for k because right now k is what we care about. So I'm going to multiply the 3 and divide by the 2. So we'll get negative 3 on 2 less than k less than or equal to 3 on 2. I'll pause there just to make sure everyone's happy with that. So what are the values of k that we care about? We know there's 3 of them. And what else do we know about k? It's an integer. So what are these on each side of our inequality? Are they integers? They're not. They're fractions, but that's okay because we just want the values of k between these 2 fractions. So we want to pick the integers. So what's the first integer that's greater than negative 3 on 2 or negative 1.5? What's an integer value greater than that? 1? Yeah, so we'll say therefore k will be equal to negative 1. What's the next integer? So we're going to be moving up in 1. 0. And then what's the next integer? 1. And then what's the next integer after 1? 2. But it's outside our domain, so we know to stop. Right? So we picked our first integer in our domain. We kept adding 1. And by the time we got outside our domain, we had to stop. How many solutions? How many values of k? 3. Perfect. So we haven't made a mistake. This is where the mistakes can happen. So that's where you're going to do that check. But whilst we were thinking about k now, what do we really care about? Theta. So we're going to put our values of k back into theta to say what are the angles. So we'll say, therefore, theta will be equal to, what's negative 1 times 2 pi on 3. So that's just negative 2 pi on 3. 0 times anything is 0. So we'll say theta will be 0. And then 1 times 2 pi on 3 is 2 pi on 3. Again, still got 3 solutions, but what else do you notice that gives us a bit of comfort, particularly about these two?
They're like negative signs of each other.
Yeah, they're our complex conjugates. And again, we see the benefit of setting up our domain this way because the complex conjugates fall out very nicely. We still would have got the right answers if we did between 0 and 2 pi. It just would have been an extra step to notice this. So now what do? We plot them. Negative 2 pi on 3, where is that going to kind of... Actually, let's work backwards from 2 pi on 3. So 2 pi on 3, what is that as an angle if we kind of converted to degrees just to help us? So 2 times 180 on 3. Does anyone have a calculator?
120.
It's 120? Okay, so if we're thinking that's 90 degrees, so we're kind of going to have to go past here, and then if that's kind of 45, so a bit less. So about there. Like it's not perfect, but it's going to be about there. Does everyone agree that that's kind of going to be about 2 pi on 3 as an angle? So that angle there, and maybe I'll note it in a different colour. This angle here is going to be 2 pi on 3. And maybe I'll erase it from up here because the point isn't 2 pi on 3, it's the angle to that point from the positive real axis. Now, it doesn't now take a lot of work because in terms of plotting this, I don't actually need to measure the next angle. I can kind of just come down vertically and know that that's the next point. And so that if I drew a line there and came back this way, it would be negative 2 pi on 3 that I'm coming back. And then the final point is the point that makes no angle with the real axis, which is that point there. So there are our 3 points now plotted on the Argand plane. Now the other thing, noting that these are equally spaced, we can also know that each of these angles is 2 pi on 3 in terms of its magnitude. They're all going to be equal angles. So far so good? Now that's the basic mechanics of finding the solutions, in this case for z to the 3. Now what I want to do is a little extra step that's going to get us to then find out an interesting geometric result. So I'll just get a new colour, maybe purple. And what I want to do, I want to link to this idea of regular polygons, the result from doing this work. So I'm going to connect our 3 points in the Argand plane. And we know that that's a regular polygon, in this case because there's 3, it's a triangle, what we often would refer to as an equilateral triangle. What I'd like to do is focus in particular on this bit that I'm shading here. And what do you think is the advantage of this particular part of this bigger triangle? What about this triangle can I take advantage of?
It's a 90 degree.
It's right angled triangle. And there's a lot of things we can know about right angled triangles. So I'm going to draw it separately here. So it's right angled. What do I know about this length here, which is the equivalent of this line? It's 1, because remember we're sitting on the unit circle. What do I know about this angle? So noting that the whole angle there is 2 pi on 3, how much is this angle, which is basically half of that whole angle? 2 pi on 3 divided by 2 is just pi on 3. Is everyone happy with that? I've made a bit of a leap there. The angle here is half of the total angle. Yeah? Because we've basically got this big triangle, we've taken half of it, we're taking half of its angle. So what can we know about the length of these sides? And for now, maybe, just for now, just to help, I might call it x and y. What do we know, or what can we say about x and y, knowing that this length is 1 and this angle is pi on 3? And I'll just write a hint. SOHCAHTOA. This is going way back to early trigonometry days. What is the sine of pi on 3 in this triangle? Y, because it's the opposite over the hypotenuse, but because the hypotenuse is 1, this is quite nice. We can say, therefore, y is equal to sine pi on 3. And what do we know about cos pi on 3? That's x. So, what do we know about the area of this triangle? Area of the shaded triangle is equal to what? What's our area formula? Again, going way back to our trigonometry. A half times...
height times base.
Yep. And so it's a half times sine pi on 3 times cos pi on 3. Now, I shaded this part of the triangle just to allow us to do some work with the 90-degree angled triangle. But actually, we care about the area of the total triangle. That's kind of the result we want to focus on. But knowing this shaded area, what can we therefore conclude about the total area? So therefore, the area of the triangle that we care about, this purple triangle, how many of these half-shaded triangles are there? 6, because 2 of these make up one of these triangles, and we know all of these triangles are equal because they've got equal sides and angles. So there's 6 of them. So the area of the whole triangle is equal to 6 times a half sine pi on 3 cos pi on 3. 6 times a half is 3. So it's 3 sine pi on 3 cos pi on 3. So we've worked out the roots of z cubed equals 1. We've put it on our Argand plane. We've done a bit of work to work out the area of that regular polygon, and it happened to be 3 sine pi on 3 cos pi on 3. Any questions at that point?